So this is going to take a look at combining random variables. So what we're doing yesterday, we talked about, if we multiplied by a constant, or even if we took our values and we maybe added a constant, how that would affect mean and standard deviation. So again, when you multiply, you'd multiply the whole thing. Both mean and standard deviation would get multiplied by the constant. So let's say if the constant were 2. If you add a constant, remember, that does affect the mean, but the standard deviation doesn't change. Here, what we're going to look at is combining random variables. So now listen, let's say that we're going to put two different distributions together, which is slightly different. So the rules for combining these things, like let's say x was, well, I'll show you an example here in just a second. If we combine random variables, so again, remember, expected value, same thing you say in mean. So this would be the mean of x plus the mean of y. And then here, if we're going to get standard deviations, we actually have to convert to variance, right? So we have to use variances to find standard deviation. Remember, standard deviation and variance are related. Variance is just the square, right? Variance equals standard deviation squared. So really, to do this, you'd end up doing standard deviation of distribution x. We'll square that. Plus the standard deviation of y. So what we want to realize here, a couple things. One, to get back to standard deviation of x plus or minus y, you have to go through and end up taking the square root after you've done that. The other thing, notice above, it went from plus or minus, we kept plus or minus. Here it goes plus or minus, and it just stops at plus. So even if you're subtracting two variables, you always add. So you'll always add variances. And notice also that you're using standard deviations in here. All right, so we're squaring the standard deviations to get there, but the big note here, we always will add variances, and the way we get variance is by squaring standard deviation. So let's actually look at an example to make more sense of this. So suppose the SAT math score is 625 with a standard deviation of 90. And on the verbal portion, it's 590 with a standard deviation of 100. So if we want to combine those, get the composite SAT score, putting those together, what are the mean and standard deviation of this composite score? So we'll call X the math score. So it's, right, again, N for normally distributed distribution with a mean of 625, a standard deviation of 90. And then we'll call Y verbal scores. So now we've got two different variables. So again, the mean of Y is 590, the standard deviation of Y is 100. So if we want to do the combined score, we need to combine X and Y together. So what is that distribution? So for us, again, if you want to kind of rewrite, this is the previous information, right? The expected score for math was 625, standard deviation 90, expected verbal 590, 100. So if I want to combine them, the combined average score, right? This is the rule that we wrote down at the very beginning, is we just add together the two expected values. So we take the 625 and 590, we combine them to get a expected composite score to be 1215. To get the expected standard deviation, right? Notice they give us standard deviation. So what we're going to have to do is convert that into variable. And the way that we do that is by squaring. I've done math out already right there. But again, the way that you're going to get variance is kind of a sidestep. So the variance of X will be 90 squared. That's where I'm getting that 8100. The variance of Y is 100 squared. And that's where I'm getting the 10,000. But currently, I'm in the wrong units, if you will. I've squared everything. So to get that back to standard deviation, remember, so variance equals standard deviation squared. So on the same note then, standard deviation equals the square root of variance. So what I've done is I've gone ahead and I've taken the square root of 18,100, and that's where I get a variation of 134.54. So the composite score, right? The expected value, right? The average score is a 1215 with a standard deviation of 134.54. So it'd be normally distributed around those numbers. And that makes a lot more sense too, right? So if all of a sudden we said, 68% of scores are between blank and blank, well, we can just do our empirical rule, right, using those numbers. That makes a lot more sense, 130, so we'd basically be between about 1070 up to about 1340, right? Maybe about 1080 up to 1350-ish. That makes a lot of sense, versus if you had to add and subtract 18,000, that would make no sense at all, right? So sometimes you might see stuff, this independent random variables, X and Y. So maybe this is amount of money on cat food and dog food. I don't know. So we'll call X money on cat food, and Y we'll call money on dog food. So, what we're being asked to do is kind of find a lot of different things. So first off, like 3x, this would be almost as if we're saying, hey, what would it be if we charge you, if all of a sudden the company says, we're going to charge you 3 times as much for food. That's what's kind of looking at there. It's really frustrating. The Y plus 6, that's like saying, all right, we're going to charge you $6 more for a bag of food, right? $6 more for a bag of food. Whoa. Excuse me, I don't know what I was trying to write there. X plus Y. We can look at that as, well, what if I have a dog and a cat? What can I expect to pay? Right? Dog and a cat. The X minus Y, I'm not really sure what that would play out to be. Maybe your cat ate your dog, but either way. And then E down here at the bottom, it's a little different look. So we have X1 plus X2. This is almost like saying we have 2 cats, right? We're not doubling the amount for food. It's saying we have 2 separate cats. And so here's how this is going to play out. So for 3x, right? So for 3x, the expected value then, if they triple the amount of money we're spending on cat food, we'd expect to spend $30. The standard deviation, if they triple our price for cat food, well, we'd triple too, right? So we take 2 times 3, which would be $6. We'd expect there to be some variation among, cat food brands, plus or minus $6, if you will. All right, now all of a sudden, what if we decided that we're going to take our dog food, Y, and the companies are going to start charging $6 more across the board? Well, that just turns into 20 plus 6. So we'd expect to start paying an average of $26 per bag of food. But if they add an additional $6, that's not going to affect the standard deviation. So we're still looking at a variation from bag to bag of $5. Now let's say we have a cat and a dog. So the expected amount of money we'd spend on food, 10 plus 20, so we'd start to expect to pay about $30 for our food. Standard deviation of X plus Y. This is where things are a little bit different. This is where we have to be very careful. Remember, so standard deviation, we can't just combine standard deviation. We have to convert to variance. A lot of times with these charts, I'll come in here off to the side, and variance is just going to be those 2 values squared. So do the standard deviation of those. We're going to add the variances, right? Remember the rule was always add variance. But to get our units back, because we just squared, so we got like dollars squared, to get it back to standard deviation, we take the square root of that. So we do the square root of 29, which is approximately 5 $5. Well, let me just calculate it real quick. Square between that will be $5.39. So we'd expect some variation, right? So 68% of the time we'd pay between about $25 and $35 for our dog and cat food together. X minus Y. This is a little bit different look at it. I don't know how to make this work with my cat and dog food scenario, but expected value, it's exactly what it seems like it should be. So negative 10. Standard deviation. This is the one you got to pay attention to, because again, we want the variances. As we do standard deviation, we have to convert to variance. But remember, the rule was always add variance, which means, again, we're going to do 4 plus 25 and take the square root of that. So this variability would be the same as the previous problem, $5.39. So you always add, you don't add standard deviation, you always add variances, which is why I've converted right there. Now this last problem, this is like we say, all right, I've got 2 cats. And really for the expected value here, each cat's going to cost me $10. 10 plus 10. You could think about it. All right, double the amount of cats. We'll pay twice as much for food. That makes sense. The one that's tricky, and what we should start to be seeing, the one that gives people the most fits is standard deviation, because you have to be careful with how you do it. You have to use variance in a situation like this. We're not just doubling. We're not saying, okay, we're paying twice as much for cat food. They're not charging us twice as much. We're saying we have 2 separate cats. So what we have to do is go, the variance for each cat will be $4. We need the square root of 4 plus 4 is the square root of 8. So for our 2 cats, we would expect, a variation of about $3 per bag. So 68% of the time, we're paying between $17 and $23 per bag. So yesterday I mentioned that the penny thing wasn't quite right. What are the reasonable likely mean and standard deviation of the 50 pennies, right? So we said X was a single penny. These things are normally distributed. For 50 pennies, that's 3.11 plus 3.11 plus 3.11, So the expected value for the 50 pennies will just be, 3.11 plus 3.11, right? We'd end up with 50 of those. We could just multiply 50 times 3.11, which we found yesterday was 155.5 grams. But I mentioned with standard deviation, it's not as simple as just multiplying by 50, right? We're not doing any kind of conversion. Here it's kind of like the cat example you just saw. It was penny after penny after penny after penny. It's x1 plus x2 plus all the way up until we get to that 50th penny. So what we need to do first, this is standard deviation, it's 0.43, which means in order to figure this thing out, we got to convert to variance. For the variance, 0.43 squared, we'll call it 0.185. What we'd have to do is add variance after variance after variance all the way up. And you think about how many of those are there? Well, there's 50. In other words, we got 50 times 0.185. Now to get back to standard deviation, remember, we're going to end up taking the square root of all that. To get variance, we'll end up doing 50 times 0.185. We take the square root of that answer, 3.04. If you think about it, now all of a sudden we'd be saying, 68% of the rolls would weigh between 155 plus 3 plus or minus 3, so about 152.5 and 158.5 grams. That makes a lot more sense than what we would have seen yesterday. Back to the insurance policy problem. Let's say that they wanted to charge you 100 times the original price, right? And we looked at this yesterday. Two different things they're looking at. One, they're going to charge you 100 times the original price versus, right, the company's trying to make a big profit, so they're either going to charge one customer 100 times more, or maybe they go out and they get 100 new policies. So which one is less likely to lose money for the company? Well, we can do the expected value and standard deviation if we charge you 100 times the original price. And that would be the expected value 100x, which is standard deviation 100x. And we look at this yesterday. That would just be that $89 times 100. So they'd look to make $8,900 if they started charging $100 more a policy. And then in terms of standard deviation, 260.54 times 100. So the standard deviation, $260,000 or $26,054. So very, very big standard deviation, right? Versus, what if they went out and they did 100 policies? So this would be expected value x1 plus x2, and they go out and they get 100 policies. Well, I don't know, $89 a pop, so that'd be 89 plus 89, right? We'd end up with 100 of those. So we end up still the same expected profit, $8,900. But with 100 individual policies, just like the 50 individual pennies or the 2 individual cats, before we can move forward, we got to convert standard deviation to variance. So up here, remember our standard deviation, $260.54. What we'll do, the variance would be $260.54 squared. So in other words, we got 260.54 squared plus 260.54 squared, so on and so forth. Well, how many of those 260.54 squares do we have? There's 100 of those. Right? In order to get back to standard deviation, we're going to end up, we have to take the square root of that. Well, here all of a sudden, we know the square root of 100 is 10. The square root of $260.54 squared is 260.54. So the standard deviation for 100 policies is a lot smaller. So what does that mean? Well, which policy is less likely to lose money? All of a sudden, we start thinking about our empirical rule within one standard deviation. All of a sudden, this policy is way in the negative right away. Versus this policy, you can see if we go up and down one standard deviation from 8,900, we're still in the plus. Actually, you have to go a few standard deviations with this policy, with a policy this way, before we start getting negatives. So which one, right? Which method is less likely to lose money? Method B. The standard deviation was a lot smaller.